Okay, all right. Mm, Give me a minute. Okay, so welcome you all once again in the last week's lecture for Introduction to Machine Learning, instructed by Professor Balaraman sir. So here we are within the 12th week. So if we take a small recap, what we have done in this session, that we have started with Introduction to Machine Learning with three paradigms: supervised, unsupervised, and reinforcement learning. So we have a great list of algorithms with us, which we have studied for supervised approach, and some of the algorithms for unsupervised approach as well. Right. So today we are going to see about the theory in machine learning, VC dimension concept, and at the last reinforcement learning. So as I already told you in the last lectures that this reinforcement learning is somehow a different concept, a different course. So we have a small concept. We will introduce the concept of reinforcement learning in these sessions. Secondly, till now what we have studied is more of a related to a practical purpose. It means where you wanted to create algorithms, where you wanted to develop models, which can be based on any application. So, for example, if I say this chat gpt model, or this a model for face recognition, and a model which can predict your weather status or something, these are all the different application which we can use for which we can use machine learning models, right? But as you all know, this the course of artificial intelligence or machine learning is one of the branch specifically from statistics and probability, right? So statistics and probability has a lot of concept of mathematics, where you prove something using some equations or theorems, right? So here also one of the key applications of machine learning arises from the theory perspective. So we will see what is the theoretical concept behind this machine learning, so that if any of you wanted to join some groups which works in especially in theoretical bounds for machine learning, you will able to grasp those concepts too. Okay, so we are going to start with theory, then at the last we will be converging towards this reinforcement learning. So this let's start with this theory of machine learning. So, in computer science, theory often refers to the problem in which we generally evaluate problem hardness. It means how difficult a problem is to solve, right? So, first thing we quantify the hardness of the problem. Secondly, which all of you, if you have a background in computer science, so when you start working with computer science, you all have been go through this concept of space-time complexity. It means whenever you are making an algorithm, its space-time complexity is very important. Why? Because in general we require less algorithm which will take less time and less space, right? Which will be quick, faster, and it stores in a very small spaces, so that you can a lightweight model which can be deploy on the edge devices also, right? Because today if you work toward this edge computing uh, thing. It means that there are very small sensors which have these AI features. So those small sensors don't have large spaces as your system PC's backups has, right? So, and everything is maintained on cloud. So it has to be transferred to the cloud. It has taken to from the cloud. So if your model is a lightweight model which is taking less time and space, then it will be more recommended to use. But you cannot for this space and time you cannot be biased towards the accuracy, obviously, right? So last thing is approximability. So approximability, it means how close solutions are to optimal. So basically when we have started in our first class, right, so we started with I told you a concept of distributions. Distributions means data. So ultimately, our main goal is to find what distribution is lying with the particular data set. So it is very difficult to approximate that or evaluate that. That's why we are using this word approximation, because we don't know what actually the data is having the distribution. We are just approximating it. Right. So these three things are very important on the theoretical computer science concept. So our main goal here is to apply similar theoretical frameworks to machine learning, because machine learning is also one of the domain in computer science which these three things will not be much diverged for the concept of machine learning as well. So for machine learning perspective, we have some key questions. So these key questions include how hard is to approximate a solution. So as I was talking about that basically, first of all, we have to find out that if you are going to approximate the solution, even we have studied about this linear regression, classification. So all of that thing are we are building to a model to approximate a solution. So is it hard or not? So that's why our first question is it a hard process to approximate this solution? If yes, then how can we simplify this process? So that's why in starting we have started with a simple optimization concept, where you can simply use mean square error, take the derivative of it, put it to 0, take the minima, it's good to go. But as you jump towards SVM or other concepts, these simple optimal problems becomes very hard. So we move towards gradient descent or iterative methods, right? So these concepts are not just taken and applied. It's more like it is analyzed in the theoretical part, and then a theory comes into picture that these methods are hard, so we cannot go for these methods. Its complexity is so much. So these complexity, how much it is complex? If it is this much complex, can we apply these iterative procedures? If these are not complex or can help to approximate a solution maybe in more time, right? So first question is how hard is to approximate this solution. Second is how do we measure this hardness of ML problems. So normally if we talk about computer science, if I ask you to develop a simple C or Python program to sort some n numbers, right? So there are multiple ways. So there are multiple algorithms for sorting as well. If I name them bubble, insertion, selection, quick, there are multiple algorithms, right? So these algorithms, their complexity can be measured in the term of this big O or omega, right, or theta. So these are the parameters in which the complexity, actually the time complexity is calculated. But can we calculate the complexity for ML problems in the same way? So can we cannot. We are going to answer these key questions in our topic in this week. So first of all, first thing we have to analyze that these sorting searching algorithm, we have a common solution out of that, right? But here it's not about solution. If we don't have just a single data and you just have to get out the solution, no, it's not like that. We wanted to model the distribution of the data. So for that, we are now going to coin some terms and understand that what are the major terminology that we can use in the theoretical ML optimization or ML problems. So first term is generalization error. So here in the theoretical concept, you always get two types of things, right? First is generalization and second is hypothesis. So or we can say that empirical. So wherever you find this term generalization, it means it is talking about a true error, because we are assuming that there is some data, let's say D, which D means it is a true distribution. So let's say I have a problem, maybe I have a problem to identify human faces, right? So human faces comes from some distribution. So that distribution which has one nose, two eyes. So the statistical parameter of this distribution are not known. We cannot know that. Obviously, we don't have any idea that this is the true distribution which can represent a human face, because all over the world there can be multiple variation of human faces, and you cannot be able to collect that data. You cannot collect that data, right? We can have multiple variation from multiple different countries, different age groups, different genders, but still you lack something in your data. So you cannot touch the true distribution. You cannot have the idea of the true distribution of the underlying data. So I am saying this D distribution is the true distribution, okay, which we don't know. So now, because we are assuming there is something true, for that we are creating this term generalization. So generalization error means E. Here the error represented by this epsilon, and wherever you find this H means hypothesis. So let me explain first what is hypothesis. So hypothesis means the model you are creating. So for example, if you have a problem to develop a model to identify a human face, right? You will use some deep learning machine learning framework. Let's say you have used some neural network framework, right? So in neural network, if you go down towards that week when we started with the concept of neural network, you have those weights which constitutes the parameters of neural network. So let's say there is a set of weights. So it means that this model with some weights is able to identify the human face. So this is called hypothesis. So this can be called as hypothesis 1. Okay. If I change some of those weights, then it will be called as hypothesis 2. Again, I create another network for the similar process. It can be hypothesis 3. In the general sense, you can understand in the form like, let's say you are here, 14 students are here, and you all constitutes of different hypotheses, right? Yes, available. The recording of this session will be available, don't worry. So basically, yes, so here you are around 18 students. So all the 18 students may constitute different hypotheses. So first student may be the one hypothesis, second student is the second hypothesis. Similarly, whatever you are creating in your model, the first architecture of first set of weights is first hypothesis, second set of weight is second hypothesis. So this hypothesis concept means the model which you are going to train, right? If that model is good or not, now question is this. So that's why we are saying that we have to choose the best hypothesis so that we can reach towards this distribution. Our main abstract goal is this. Okay, so the ultimate goal of any machine learning algorithm is you have to choose that hypothesis which can lead towards this true distribution, right? Question arises, ma'am, we don't know about the true distribution, how we can say that we are approaching towards that? So that's why, because we don't know it, we say whenever in mathematics we don't know anything, we say suppose we have this, right? So we start with suppose, we end up with formulating some formula that can lead us towards this unknown thing in our mind, right? So here also we are saying that we are defining this error, generalization error, over this true distribution. So what is generalization error? That's why it is written epsilon for hypothesis H, because you have to have some model so that it can create this approximate this data. So for the hypothesis H, the generalization epsilon is defined as
Ma'am,
any.
your madam, sorry to stop. Your voice is breaking a lot today. I mean, in between, we are losing you a
Okay,
bit
okay.
today.
Hello, am I clear
Yeah,
right
yeah.
now?
I mean, you are clear, but in between, it is breaking. So,
There is no seamless connectivity, ma'am. Your
yes, yes.
voice is breaking, and we are able to hear very faster. I mean, two
I'm
times
not
or three
able
times than
to
your normal speed.
get the concept. Yeah.
Okay, let me be somehow slow. Okay, okay. Or let me be reconnect again. Can it be possible? Okay, if my voice breaks again, then please let me know. Okay. Okay, network stability is somehow, I think. Hello, now is it audible?
Yes, you are audible, ma'am.
Hello, hello, am I audible?
Yeah, yeah, you are audible.
Let me reconnect. Hello, am I audible now? Hello, hello, am I audible?
No, ma'am. Ma'am, your voice is breaking. Voice is not clear, actually, ma'am. We are listening, but voice is not clear. It is actually echoing or superimposing something like.
Oh, hello, am I audible? Okay, thank you. So let's start again. So I was talking about the theoretical bounds here. So especially in computer science, we formulate the hardness or the complexity of the algorithms or the problems to how much hard is a problem to approximate this solution, right? So in machine learning also, initially the goal was to approximate the data distribution, the true data distribution. So for that, first we will define some terms, right? So the terms include, first is generalization error. So wherever you find this term generalization, it means it is directing towards the true distribution. So let's say I was giving you an example that let's say your problem is to create or develop a model for identification of the human faces, right? So there are multiple types of human faces on the basis of race, gender, color, uh, caste, creed, countries, maybe many things are included for the facial features. So you cannot include a data set which can give you the true distribution. Secondly, you don't know about the true distribution in advance, right? So whenever we don't know anything, and in mathematics we say, let us suppose it is some variable d which we don't know. It has some parameters but we don't know about that. So can we start with this unknown thing and have some idea that how to approximate it with a good probability, you can say, right? So here in generalization error, this error is defined with this variable epsilon. And epsilon of what? Of the model or hypothesis. So this hypothesis means the model that you are developing. So maybe the first student has used some architecture, optimize it, has some weights, that is your first hypothesis. Similarly, second student has different architecture, different weights, second hypothesis. So it means that the hypothesis is nothing, it's just the model with the set of parameters defined previously, right? So let's define this generalization error. So what does generalization error say? It is the probability that hypothesis H makes a mistake on a new data point xy sampled from distribution D. So here this distribution D is true distribution. It means that any of the sample around the world, if I pick any sample and you have some hypothesis, so what is the probability that your model will make mistake? I am not saying this is the simple error, but I am talking about the probability, right? So if you talk about the probability, you are not saying a particular sample, you are talking about on average what will be the error in this model, you can say like that. So that's why it is called generalization error. So it is defined as this hx not equal to y, means this is called error. This is the error, and this x and y is coming from distribution D. It means it is coming from the actual real data around the world, right? So it means that this is your generalization error which is to be minimized. We wanted this to be minimized, but to solve that, neither we have D, we don't know about D. We can have x and y, we have the real data all over the world, but first thing, we don't know anything about D, and we cannot have all x y so that we can approximate this probability. So this is very what you want to say is more like this generalization error cannot be calculated. So now if we don't calculate this, let's go towards the approximate error. So approximate error is empirical error. So empirical error, that's why it is defined with this cap. So this is your generalization error, I define it with cap, which is called empirical error. So empirical error say कि the error measured on training data is called empirical error. So that's why this training data is very important, right? Because we don't have whole data all over the world. So that's why we collect some of the sample data, which is called as training data, and we calculate the error using the hypothesis on this data. So this data, which is the sample from the whole distribution, which we don't know, that's why it is called as empirical error. So this empirical error is defined as simple mean square error, you can say. So that's why it is written as 1 by m. So you calculate, you train your model on this data, you calculate the average error, and that is called as empirical error. Now question arises, is the empirical error same as the generalization error? So the answer is no. It is not same. right? So it cannot be possible that empirical error and generalization error can be equate to each other or equal to each other. No, but we wanted to have that data in our system so that this empirical error can move closer to the generalization error, we can say. We wanted to say that. So for that purpose we have to define some more things. So that's why the challenge is here ki the estimation of this generalization error we can estimate it only using the empirical error. So it's just that in our hand we have the empirical error, but our goal is to minimize the generalization error. So we have to move this empirical error closer towards this generalization error and then minimize it. How to do that? Let's see this. So to aim this goal, we have empirical risk minimization formulation. So what we do is, this empirical risk means this empirical error. So empirical error minimization, generally what we do optimization on this empirical error. So most of the learning algorithms which you have studied till now, they aim to minimize this empirical error. So what you have done in linear regression, you have done the same thing. Argmin, where you have applied this, you can treat this h as theta, right? So we wanted to optimize those thetas or weights, you can say. So those weights or thetas are optimized using some algorithm of optimization, using that minimization, that is also called as empirical risk minimization. All right, so generally we do that. It's not a big issue, but now we have to theoretically prove that how this formulation is good for us, and it can lead to the minimization of generalization error as well. How we can say that? So for that they define some more things. Here first they define hypothesis class. So hypothesis class, capital H, say that there are multiple hypotheses, H1, H2 and so on, K maybe. So there are multiple hypotheses which can be applied to solve a problem, right? So if you are saying using this a formulation, when you start with linear regression, what you do that you optimize these thetas, right? So let's say first set of thetas, initial set of thetas constitute h1. When you optimize in the first step, one iteration, after the one iteration completion, it is h2, maybe next iteration completion it is h3, and similarly in k steps you get kh, yani ki this hypothesis class is the set of all hypotheses which can be applied on the problem to solve the to get the approximate solution. Now you have multiple type of classifiers that you have already defined. Some linear classifiers, neural network classifiers with parameters theta and their architecture, right? So ultimately these hypotheses are dependent on these classifiers, you can say. So practical issue is this this minimizer, this ERM may not find the true minimizer, right? So because this was the major challenge, that okay, you have the data, you have some hypothesis, you can get good hypothesis on your training data, but how can you be sure that this minimization is good for all the data related to this problem around the world, is equally important using this minimizer. So to do that, let's have some theoretical tools. So for those theoretical tools, we have two things that we have to keep in mind. So these two theoretical tools are very important. Maybe you can have some questions on these theoretical tools also, because these tools are in your lecture videos as well, right? So it's a simple theoretical concept that maybe you know before that also, but let's recap this. Okay, so first thing is union bound. So they say that if there are k events, a1 to ak, so what is the probability of union of k? It means that, let's say this is your event a, this is your event b, a1, this is a2 and a3. Okay, and you have to calculate the probability of all the events, all these three events. Okay, so what should be the probability? Let's start with maybe two cases. It can be easier for you. So these two, this is A1 and this is A2. Okay, and this is their intersection. So if I say A1 union A2 using a formula, we know that A1 union A2 is A1 plus A2 minus A1 intersection A2. So probability of A1 union A2 can be defined as probability of A1 plus probability of A2 minus probability of A1 intersection A2. Why it is intersection is minus from this? Because if you are adding A1, if you are adding A2, then this intersection add two times, right? So we have to deduct it one time, which is repeating. So that's why we can say that you cannot just sum the different take the sum of the individual events. If you are talking about the union, what you have to do, you have to subtract it. So I can also write it like that: this probability of A1 union A2. Okay, this term, this P of A1 is positive, this P of A2 is positive, this P of A1 intersection A2 is positive. So let's say it is 0.9, it is 0.8, and it is 0.5, right? So it means that these two numbers are added and this is subtracted. So ultimately, the right hand side, you can see here, the right hand side, this sum is much more than this single summation, right? Just think about this: something is subtracted from the individual sum. So ultimately, this whole probability will be less than or equal to P of A1 plus P of A2. So this is what it is written from here also. So what we can say that the union of the probabilities of all event is not equal to the simple summation, but less than equal to the summation of individual probabilities. Okay, why it is less than? Because this union will consist of some subtraction of their intersections part as well. So that's why this union will be less than equal to the simple summation of all the events, right? So let's say if you have two events, A1, A2, A3, if you want to calculate the union probability, then take the summation of individual probability. It will be the upper bound for that. इससे ज़्यादा नहीं हो सकती, but it will be less than from that. Okay, so this is your first theoretical bound. So maybe the question can be like that: you have two events, A1 and A2, and some question is more like what will be the probability of A1 union A2. Okay, so is it greater than, less than? It can be written like that, right? So this is a first theoretical concept that we are going to use in the another slides. Second is Hovding's inequality. So Hovding inequality say for IID means identically and independently distributed. So let's understand this IID concept first. Identically and independently means, let's say you throw a dice, right? So there are 6 outcomes, 1, 2, 3, 4, 5, 6. So it means all the outcomes have same probability, nothing, no outcome is biased. So it means that identical, right? So identical means all the outcomes have same probability. Second is independent. Independent means it is not like that let's say if your dice has some bias in the form, if one is coming, after that it's only chance that 2 or 3 will come. It is not like in your dice, right? So it is, all the outcomes are independent from each other, and the probability of each and every outcome is identical, is same. So that's why we generally create the samples which are IIDs, identical and independently distributed. Bernoulli random variables means binary. It means you have m experiments, 1 to m, and the variables can have the probability which is binary in nature. So the outcome can be 0 or 1, right? So let's say it's head or tail. So you are just tossing a coin whether it is head or tail, first time, second time, mth time. So they say that for these type of random variables with mean phi, so this phi is true. because we don't know about the true mean, we are saying another mean which is called this phi cap, which is empirical mean. So think about this. I told you the last slide. If it is written as simple mean, it is like generalized mean, and this is your empirical mean. So our goal was, if you are talking about mean, it can be written in the form of error as well. So they say that for any distribution, this is your true distribution mean and this is your empirical distribution mean. And they say that, let's say we have some tolerance gamma. Tolerance means the difference between the empirical and the generalized mean. So it means that that was our main goal, that whether this empirical error is close to the true error or not. So we are saying, because we don't know, let's assume that the difference between these two error is gamma. Okay, that's why it is written as phi cap minus phi is greater than equal to gamma. Greater than gamma means the error will be at least gamma. इससे ज़्यादा ही होगी, इससे कम नहीं होगी, right? So if we are saying that this gamma is 0.8, it means high error. If I am saying it is 0.1, then it means that it is low error. Maybe it can have low error, but it is a greater than sign. So basically I'm saying the difference between these two error is greater than equal to this gamma. If I am saying this tolerance, I am tolerating this much gamma. So the probability of this, right, the probability of this high error, this is called high error because it has a greater than sign, right? The probability of high error should be less than something. Okay, so this is the inequality which is written in literature. You can find the proof as well, but I am not going to discuss about the proof. It's just that we are going to use this inequality. So this will be less than this number. So this number has two exponential gamma and m. M means how many hypotheses are there, right? And sorry, m means number of samples are there, and gamma is defined by this tolerance. So it means that it is saying the probability of this high error is less than this term. So this term, let's say I am denoting this term as delta. So this delta is called as failure probability. Why I am telling this as a failure probability? Let's say this delta is 0.9. So it means that this is high error. High error should be less than equal to 0.9. So it means that the error is this high error, the probability of this high error should be less than 0.9. So upper bound is 0.9, but it can be 0.9. So it means that there are 90% chance this error is so much high, right? Ab this probability, let's say, is 0.01. So it means that the probability of failure is 0.01. It means the probability of this high error is less than 0.01. So it means there are less chances of this high error, right? So that's why we wanted to calculate this probability, that how much empirical error is different from the mean error. So now if you don't have this actual true error, but we can define the tolerance around the error. So how I am formulating the problem, which I don't, if I don't know anything about the true distribution, just understand in the form that if I am asking you, okay, this is the problem and you have to solve, okay, and I don't know the actual answer, I don't know, okay, how much is the correct answer is there. Now you are here 18-20 students, all of you are giving me some answers, right? So let's say there are 20 students and 20 students are giving me some answers out of it, right? Those answers will be having some error because I give you some of the data, right? Some of the data I have given to you, and on that data you are saying, ma'am, my model is 80% accurate. Some say my model is 70% accurate. Some say my model is 30% accurate. So this is your own models, right? And you get an error on your data. Now I don't have the actual data, so I am not able to say that among which of your model will be the best that can be deployed in the market, right? Because let's say this data has some bias, so this data cannot be used for that. So what I will say, because I am not very sure, I want to calculate a probability ki, let's say from your error, there is a tolerance. I want to give a tolerance ki let's say the actual model and your model has a error of let's say 0.8, right? So this tolerance I want to define. This I can control, this I can define. So if I wanted to calculate the probability, if your model and the actual model, actual true data has the difference of error of 0.8, then what will be the chance that how much probability your model will be able to approximate the solution. If this difference, this tolerance is 0.7, then what is the probability? What is the probability for 0.6? What is the probability of 0.5? So I want to choose that stable model that can reduce this effect and give me high chances that this error should be low. So that's why this Hovding's inequality is very important. So how we are going to define this? So we are saying, as I told you, you are here 20 students and you are all 20 students are going to give me the answers for the training data that I have given to you, right? So those 20 means K hypothesis. You can say here K is equal to 20 in the example that I gave you, right? So for all K hypothesis, because you all are so much well developed to solve the problems, so among you all I don't know the actual answer. So what I will going to do, I will calculate the probability according to your union, right? So that's why we first understand this union bound. So what I am going to do, I want to calculate this probability for all of the hypothesis. So it means this union of the hypothesis, K is equal to 1 to K. Okay, so for all the hypotheses, I want to calculate this probability of empirical error and generalization error is greater than gamma. This I want to calculate. So because this Hovding's inequality calls this procedure for single hypothesis, I want to calculate it for all the hypotheses, right? So for all the hypotheses, the union has this formulation less than equal to the summation, and it is also less than equal to. So we can combine this less than equal to. So it means that for hypothesis 1, the formulation will be less than equal to 2 e to the power minus 2 gamma square m. For second also it will be like this. Third also it will be like this. So how many times you are going to add this? K times, because there are K hypotheses. And there is no parameter here which is dependent on any other variable. So it means that we can just combine it. It is repeating K times. So that's why it is multiplied by K. So these two things, why I have included in the starting, because I wanted to find the probability union of all hypothesis for this high error between the generalization and empirical. So it means I want to calculate the probability of the error between the empirical and generalization for all the hypotheses. That's why for all hypotheses union thing is going to be used, and for the difference between the empirical and generalization error, this Hovding's inequality will going to be used. So what we are going to do, we have just formulated this equation for all the hypotheses. We are saying the probability which for any h that violates this assumption that the difference between this is less than equal to gamma, gamma is the tolerance limit, that probability will be less than equal to this number. Okay, so this number हम पहले से बोल चुके हैं, let's assume this number be delta. Okay, so when you are going to use this delta, because I want to calculate this gamma also, right? This gamma and this thing, I want to calculate a relationship with this, so which can be helpful for us. So what we are going to do, this we are taking this term as delta. This delta is failure probability. If you solve this, think about this, this delta is equal to 2k e to the power, this is the same thing that we assume that, and we wanted to calculate now gamma is equal to something. So how we can do that? We can simply solve it. Just take e to the power to the left hand side, so that its power will be in the positive side, and to remove exponential, we convert it into log, and we can calculate this gamma. So this gamma is dependent on this failure probability, this number of hypothesis, and m. And if you shuffle idhar udhar, okay, so you can calculate this either gamma is equal to, you can calculate it as delta is equal to, you can calculate it as m is equal to, you can calculate it as k is equal to. In another sense, I can say that these four parameters are very important. If any of the three parameters are given to you using this formulation, you can calculate the fourth parameter. So why this is important? Because they are saying that if you know about the tolerance, if you know about the failure probability, if you know about the number of samples, and if you know about the number of hypotheses, you can have an idea that if your empirical error is close to the generalization error or not. So what we can say that, let's say we generally, the question comes in this form that one question is there. So this is your formulation with respect to m. अभी तक हमने निकाला था with respect to gamma. This is calculated with respect to m. So the simple question is, let's say for k is equal to 100 hypothesis, where delta is equal to 0.05, this is the failure probability, and gamma is 0.01. It means I am saying the tolerance, let's say your algorithm is so good and your it is different from the actual error by the tolerance of 0.01 only, then how many samples are required? Generally, this question is related to how many data samples you require so that your training data can mimic the actual data. So as you increase this gamma, you will see, as see here, as you increase this tolerance gamma, the m will decrease, right? It is inversely proportional to it. Means that if you allow more error tolerance, you need less data, but if you allow less tolerance, it means that the m should be very higher. So let's say your tolerance is 0. If I say I wanted to calculate exact true distribution, true error, so it means you are saying the difference between the empirical error and the generalization error is 0. If gamma is equal to 0, then m becomes infinite. So it means you cannot have infinite number of data. It is not possible. So that's why we put some number close to 0, and we wanted to find out that how much data you require for these type of hypothesis or with number of samples. So this number of samples is very important. So, and this is generally for the theoretical point of view. So we can have this minimum, these number of samples should be there. So this will give you the minimum number of samples with all other parameters. So this k should be known, means number of hypotheses, this failure probability should be set, and this tolerance is to be set. So according to that, you can have, for example, they are saying for 0.05 failure and 0.01 tolerance and 100 hypothesis, you require at least 30,000 samples. So just think about this, if you need a good formulation or good approximation, you need these much samples in your data to train only, let alone testing and validation, let alone that part. To train your system, you need this much type of number of samples. So think about that, the number of samples which we are getting in our life, 100, 200, how much that model will be able to deploy in the real world, right? So this is the beauty of this theoretical analysis, we can say, right? So the more you get good results from theoretical analysis, the more surety you will have that your model will work in the real field. So at present, whenever you are going towards the research of in this machine learning domain or deep learning domain, yes, presently many of the testing part is based on many application and model analysis. But if you are including any theoretical concept, then means it's more like it will be accepted, your work will be accepted as soon as possible. Okay, so that's why this all these things are related in theory as well. So if you have any doubt till now, then please go ahead. Okay, voice is breaking. What should we do?
Ma'am, ma'am,
Let me change my place then. And please switch on your mic, because when I am on the slides or PPTs, I'm not able to, see these messages. So let me change the place.
ma'am, can you hear me? Ma'am,
Hello, Shreya ma'am. Are you able to listen?
Hello. Am I audible now?
Yes, ma'am, you're audible, but your voice is continuously breaking. There is no seamless connectivity.
Okay. Still also, I have changed some place.
it's now fine now, ma'am.
Okay. It's a request that please, all of you mute yourself. If you have any doubt, then only unmute. Sometimes there is some echo from the speakers as well.
Okay, ma'am.
Okay. All
Ma'am,
right.
I have a doubt. Ma'am,
Yes. Go ahead.
ma'am, in the union thing you explained right, ma'am, but like union of a variable, I mean, union of a from the where we have like k variables.
Yes.
There is it to avoid repetition of variables when we do some calculation?
No, there will not be repetition of variables. There will be multiple variables, and it is not simple variables. These are random variables which you can associate with some events. Okay, so for example, A1 is associated with, let's say, a event showing 2 on a die. This is one event. This is A1. A2 can be the event which is showing 4 on a die. So you define those events. Now I wanted to have a union of A and this A1 and A2. So union means either on a die it is 2, or either on a die it is 4. It's more like that.
But in case of union, we will not have repetitive events, right, ma'am?
You can have, look, repetitive events, ultimately we don't define repetition in the events. If you are saying A1 is, A1 is defined as the event having 1 on a die. If this event is defined, you cannot repeat it as A2. A2 is also same as A1. No, you cannot define. We never define like this. Yes, we can define like A1 is 2 on a die, A2 is either 2 or 4 on a die. These are two different events, we can say. But if you have defined A1 as 2 on a die, 2 on a die single will not be defined again with any other name.
Okay, ma'am.
Okay, all right. So let's start with next concept. So basically, what I want to say is it again breaking?
At least not now.
Sometimes it is breaking, ma'am, when you are in the flow. We cannot say
Okay.
when are you breaking. We cannot predict. Again, you
Okay.
have to use some machine learning
Okay.
tools.
Okay, so generally we have this problem when the mics are open at the both side, right? So please try to switch off your mic. If you have any doubt, then only switch on your mic. Okay.
Yeah, of course, ma'am. We're doing that.
Okay. Okay. So basically, let me recap what I wanted to say here, that here we have defined this all this thing just to get this equation. Okay, so this equation is very important, as this can allow you to define how many number of samples you require to have a tolerance of gamma with the failure probability of delta and with these number of hypotheses. So if you know all this, you can have an idea that okay, let we have this much data in our hand for training, so that our empirical error can be close towards the generalization error. So the more close we wanted to go, the more number of samples we needed. So this formulation is important. This formula you need to be remember. Maybe some question can be asked for that. Okay, next thing is VC dimension. This concept is also very important. This VC dimension means Vapnik Chervonesky dimension. It is defined by these two scientists. So that's why it is called VC. And it is a measure of the complexity of a statistical classification model. So because one of our key question was how to define the complexity of ML models. So this is one of the way, VC dimension. And how we define is, we define in the terms of its ability, means the ability of the model to shatter data set. Now important is, what is this shattering? Let me explain that. So before coming towards the concept of shattering, first of all we define a hypothesis space. Hypothesis space, capital H. So this capital H is the set of all possible functions or classifier that a model can learn. It means that if I am talking about SVM, this is one classifier, this one, maybe this is another classifier, this is third classifier, this is fourth classifier. So there will be infinite number of classifiers can be there, right? So it is the set of all possible functions. For example, in linear classifier, all possible straight lines in 2D that can divide the space into two classes. So this is also a linear classifier, and all the possible straight lines can be the set, can be included in this hypothesis space, a set H, capital H. Now, what is shattering? Shattering means a hypothesis space shatter a set of points if it can correctly classify all possible labelings of those points. For example, if I am saying, let's say I am in 2D, okay, and there are 3 points, or let's say there are points only. This is one point and this is another point, right? So they are saying, if a hypothesis H, it means if a line here, because I am in 2D, if a line can shatter means correctly classify all possible labeling of those points. So for these 2 points, there are only two possibility for binary. If I say this can be +1, or this, look, there are 4 possibility. It can be, both can be plus, both can be minus, one can be plus minus, and another can be minus plus. These are the 4 possibility. If all the points are plus, the line can be drawn like this, right? If both are minus, then again the line can be drawn like this. If it is plus and minus, the line can be drawn in between. So it means that the 2D line, any 2D line will separate these 2 points easily. There will be no issue, right? So that's why it is written that hypothesis space shatter a set of points. Set means I am defining this set. How many number of set? It means n points. If it can correctly classify all possible labelings of those points. So any number of possible labelings, if any line can classify it correctly, it means this hypothesis can shatter these 2 points easily. No problem with that. So that's why they have written, for n points, there are 2 to the power n possible ways to label them. As I told you, For binary classes, there will be 2 to the power n. If there are 2 points, there are 4 ways. If there are 3 points, there will be 8 ways. If there are 4 points, there will be 16 ways. You can define plus or minus. Okay. If your model can classify all 2 to the power n labelings correctly using some function in the hypothesis space, then it shatters those n points. So that's why we wanted to know that how many points these hypothesis class can shatter. I am not talking about single hypothesis, I am talking about set of hypotheses. It means that what I am saying, let's say this is a function, these are 2 points, so maybe this can be 1 h1, which can shatter 0 1 or 1 0. Okay, this is h2, which shatter if the points are 0 0, and this is h3, which can shatter if the points are 1 1. So h3 shatters this point, h2 shatters this point, and h1 is going to classify these points. So it means that h1, h2, h3 are in the set of this capital H. So that's why it is written some function in your hypothesis space. It means for all the labelings, for any rule of the labeling, some of the function will be there which can uh, uh, correctly classify these labels. So then it is called as these lines or these hypothesis class is able to shatter those endpoints. And what is VC dimension? The VC dimension of any hypothesis class, it is not of single hypothesis. VC dimension is of hypothesis class, is the maximum number of points that can be shattered by hypothesis class. It means how many points it can shatter. For example, let's say we have linear classifiers in 2D. Okay, so in linear classifiers, let's start with point 1. This is a single point. Okay, if it is only single point, there are two possible ways, whether it can be plus 1 or it can be minus 1. It is plus 1, then maybe this can classify this. Okay, if it is minus 1, then maybe this hypothesis class can classify this. So it means that this single set of points, these set of 2D lines or linear classifier can be shattered. Data set can be shattered. Okay. Now this is for n is equal to 1. Let's check for n is equal to 2. For n is equal to 2, there will be 2 points. I gave you the same example here. For these 2 points, if it can be both are plus, then this can be the line. If both are minus, this can be the line. If plus minus or minus plus.
Your voice is breaking, ma'am. In between.
Okay, let me again connect. I don't know why it is happening. In fact, I don't have any device around me.
Your presentation has gone, ma'am. And your speed is increasing, ma'am. Voice speed. We are able to listen twice or thrice than your normal speed.
Now check, is it audible now?
Yes, you are audible, ma'am.
Okay, I have removed all my stylus and all. So let me again connect it. Okay. Actually, speed is more like if the voice is breaking, it recovers with the help of speed. So all the words that I have spoken, it's more like it will be repeated but in the fast speed. Maybe it's happening like that. So let's reconnect. So till here, is it clear that this hypothesis space and shattering?
Can you repeat it once?
Okay. So basically, what we are discussing here is VC dimension. So VC dimension is the measure to is, measure the capacity of this machine learning classification model in terms of shattering the data set. So what is the meaning of shattering? Shattering means, let's say you have a hypothesis space. If I am talking about hypothesis space, it means it is a set of hypotheses. I'm not talking about single hypothesis. So a hypothesis space can shatter a set of points. Set of points means there can be n points. 1 point or 2 point means I want to ask how many points this hypothesis is able to shatter. Shatter means correctly classify. So correctly classify, it's not simple like that ki correctly classify. It should classify all the possible conditions on those set of points. For example, if I ask you ki let's say I have a data set with feature 1, single feature, right? So if I am talking about a single feature, so that single feature is not sure, it should not be single feature. It, your data set has only one type of samples in your data. So it means that for the single type means either it can be positive or it can be negative, right? So this is called n is equal to 1. For n is equal to 2 means there are two samples. So those two samples can be, one can be positive, another can be negative, or both of them can be negative, or both of them can be positive. It means I am talking about what can be the possible classes for n number of points. So if the hypothesis class can classify n points, then its VC dimension is n. So for example, let's say, first of all, define the hypothesis class. So hypothesis class, they define it here for this example as any 2D line. So that's why I make this 2D space, right? Any 2D line. So line is your hypothesis class. Now let's start with n is equal to 1. So for n is equal to 1, it's very simple. Any line can classify it in either in the positive case or in the negative case, no problem. Okay, but let's talk about n is equal to 2. So for n is equal to 2, there are four possibilities. So for the four possibilities can be, both the points can be positive, or both the point can be negative. If both the point can be positive or negative, then it means a single line can be there. If one of the point is positive or negative, then we can draw a line in between them. It means any set of 2D line can help to shatter these 2 points easily, no problem. Let's talk about 3 points. So these 3 points, these three points, and these 3 points can be any point on this whole space. It can be like in the form of a collinear line, it can be in the form of this and this. So you have to think about all the possible situations where these points can be shattered by the line or not. Okay, so for these three cases, this example is there. For all these three cases, let's say for case 1, if all 3 points are belonging to red yani minus class, -1, so it means this classifier can be drawn. If one of them is belonging to a positive class, then this classifier can be drawn. If this can be the positive, this means there are total 8 combination, and you can see from all these 8 combination I am able to simply classify these points in the 2 classes easily. Okay, so it means for any 3 points, these lines, 2D lines, are able to classify it. Then n is equal to 2, for n is equal to 3, it is shattering the data set. So it means till now VC dimension is 3. But think about n is equal to 4. It means there are 4 samples, 1, 2, 3 and 4. So can you define for this case? This is 1, this is -1, and this is 1, and this is -1. So can you have any line which can shatter this combination? Yes or no? For this combination, I have written here any line, any straight line, single straight line can classify this combination, yes or no?
No, ma'am.
Correct. So it means that this set of 4 points cannot be shattered by 2D lines. So if it is not shattered, we stop here and we say that VC dimension of any 2D lines, means linear classifiers, is 3. Okay, so this is how you calculate the VC dimension. Okay, so next example is also shown here. Now the hypothesis class is like an interval. So interval means, let's say, any doubt, 1 and 8 looks alike. 1 and 8, yes, 1 and 8 looks alike because red means -1, blue means +1. The class is binary na, so that's why it is look alike. The colors are different. Okay, yes, Sudhakar has raised the hand. Any doubt?
Yeah, yes, ma'am. Just now you have clarified why that 1 - 1, how that values you are taken, ma'am.
I'm talk I am talking here about binary classifiers only.
Okay, okay.
Okay, so because I am talking only about binary classifiers +1 and -1, that's why I have written there are 2 to the power n possible ways. If there are multiple k number of classifiers, then there will be multiple combinations as well. You cannot say 2 to the power k only, right? So because let's say if you are saying that there are 3 classes, then your combinations will increase and you have to think about all the combinations. Okay, so it's more like that. Presently it is I'm talking about binary. Next is I am defining a hypothesis on the basis of interval. Interval means a straight line is there and interval is defined like this. So interval, this a point and this b point. So that's why the interval is defined h of x is equal to 1. It means inside the interval it is 1 and outside the interval it will be 0. So the hypothesis of x is equal to 1 if x lies between a and b. That's why it is written, right? So can you tell me that if on this line, because it's a line, that's why it is on the real line, the interval is on the real line, if only single point is there, it will be either 1 or 0, right? If it is 1, then it should be inside the bracket. If it is -1, then it should be outside the bracket. So it means 1 point can be shattered by this type of class, no problem. For 2 points, this one and this one, for 2 points it is also easy. Why? Because if both the points are 1, then it should be inside the bracket. If both the points are 0, then it should be outside the brackets. And if one of the point is 1 or 0, then that point can be that can be put inside the bracket and another one can be outside the bracket. It means 2 points can also be shattered, right? Can you tell me 3 points can be shattered or not? Or if it is not shattered, which combination it is not able to give you the answer? Single classifier means single bracket should be considered only.
Ma'am, since it is a binary class, it should be possible, I think.
No, it is not. Just
Ma'am, when there are two numbers in one group, then maybe it is not possible. Like 0, 1, 1. Then for this, it is not possible. Maybe.
101 it is not, 011 it is possible. For 011 both will be inside the bracket and 0 will not. It will be possible. If it is not possible for only this case 101, because 1 and 1 are outside, we cannot put like that. This cannot be there because 0 is inside, and two brackets we cannot use. Clear? Understandable?
Yes.
Okay, so it means for 3 points this these intervals will not work, will not shatter. So VC dimension of this class is 2. Okay, so similarly your hypothesis can be anything. For example, your hypothesis, I have taken 2D lines. Second, I have taken interval, right, inside A and B. Third, you can take a square of size A, right? Of size A, square is there. Inside the square it is 1, outside the square it is 0, right? And you can take a rectangle, or you can say there are क्या कहते हैं, what you can say, the hypothesis is more like that, where you define multiple intervals, right? Not single interval but multiple interval. Okay, let's say you define A and B is one interval, C and D as another interval. So those two intervals can be applied here. So if two intervals can be applied, this 101 can be shattered, no problem with that, because we can apply two intervals, no problem. But for single interval we cannot use that. So ultimately, if some hypothesis is given to you, you have to tell that what is the VC dimension of this class. Okay, so now question arises, why this VC dimension important? So why this VC dimension important? Because a model with very high VC dimension may fit the training data well. It's so simple. If I am saying, for let's say these n are number of samples, if I am saying some hypothesis class has VC dimension of 30,000, it means it can simply say 30,000 samples can be easily classified, right? So if 30,000 samples can be classified with this hypothesis class, then it means your training data is good. Okay, so low training error will be there, but fail to generalize. Why? Because very high VC dimension, it means, just think about this, if the VC dimension is 30,000, then your model is somehow prone to overfitting. So if you can see here, these VC dimensions are applied on the basis like these brackets, right? So if I say for these brackets, if I say there are 30,000 n is equal to 30,000, these brackets are good to go. So you will say it means there are many brackets will be going to use, obviously, right? So it means it has some issue of overfitting. So from this VC dimension, in theoretical way, I am not talking anything about practical. I am just talking just on the basis of theoretical ways, can we associate some meaning of these words or not. So these terms are in theory of machine learning, not in practical way, right? So a model with very high VC dimension may fit the training data well, but fail to generalize. That is a problem of overfitting. Or we can say that in practical, if we are having this overfitting issue, then obviously the VC dimension was high for that case, right? Secondly, sample complexity. So this VC dimension tell you how much data we need to learn. So ultimately this is another formulation that for any hypothesis class with VC dimension D, the number of training samples required for good generalization is like this. So there we have calculated M, right, with the help of generalization error and probability and tolerance. Here we are calculating with the help of VC dimension. So E is your same error tolerance and D is the probability bound, delta. Delta means failure probability. It is same. But here now this VC dimension is used in place of K. So if you don't know that how many hypotheses are there, then you can use this VC dimension to calculate the complexity of N. So there was another formulation here. is one another formulation for the number of samples. So let's say you have a question where tolerance limit and failure probability is given to you. Secondly, VC dimension is given to you rather than the number of hypotheses. So you can use this formulation in place of that one to calculate the number of samples. Okay, so that's why this VC dimension is important. So now there is a concept of PAC learning. PAC means probably approximately correct. So just think about this. Before this, we defined the formula in the form of E star minus epsilon. This bound is greater than gamma, right? And this probability, this P, we defined as less than it is upper bound is greater than equal to delta. This we have defined from the from these 3-4 slides back, right? So just think about this. This is talking about correctness, so that's why it is called correct. Secondly, it is defining some tolerance here, right? This tolerance. So tolerance means it is not accurate, it is approximate. So this is approximate. Second is probability is calculated. So that's why it is written as probably. So PAC learning defines this rule, which is known as probably approximately correct. So if you can define this error term in this way, it means that this PAC learning, or we are talking about probably approximately correct. So this learning is a formal framework that helps us understand when and how well a machine learning algorithm can learn a concept from data. So in this way, if you have some data and you can put some calculation here and calculate the probability, and this probability is quite low because this is the failure probability, right? If this comes very low, it means that algorithm is better to go. It's more like that, right? So the idea is a concept of PAC learnable. So we wanted to define the hypothesis is PAC learnable or not. So the concept of PAC learnable, if with high probability, right, a learner can find a hypothesis that is approximately correct using a reasonable amount of data and computation. So just think about this. We calculate m is equal to in the terms of delta, gamma and k. So that's why it is written as reasonable amount of data. Computation, it is written because some probability is there. Second thing, it is approximate solution, it is approximately correct, and it is talking about the hypothesis with high probability. So here this high probability means success probability. So if it is written as high probability, we are talking about 1 minus delta, not delta. Okay, so we want to find a concept that if a concept, or you can say algorithm is PAC learnable. Why? Because it is giving a high probability the learner can find the hypothesis that it is approximately correct using some reasonable amount of data and computation. It means this hypothesis class concept means this hypothesis class has those learner which can able to give you a good approximate solution, a good approximate hypothesis. So that are called as PAC learnable. So PAC learnable means if this probability is high, this tolerance is low with reasonable amount of data. Yes. Hello. Okay, so this is called PAC learnable. So here also they have written all of that thing that I have discussed right now. So you can go through that. It's the same thing. So its relationship with VC dimension, we can say that VC dimension play a central role in PAC learnability. Why? If a hypothesis class H has finite VC dimension, finite means it has number 2, 3, 5, 7 something, then it is PAC learnable. And the number of examples need to learn grows with the VC dimension. Obviously, as the VC dimension grows, the number of examples obviously will be growing because this is the formula. this was the formula, right? So as the VC dimension, this is the VC dimension is directly proportional to the n. So if VC dimension is more, then the number of samples required is more. Okay, so here are some VC dimension of some classes. For example, threshold in 1D. 1D means you are saying greater than a, then it is, for example, the x is greater than a, then it is 1, otherwise 0. Okay, intervals in 1D, linear classifiers in 2D, that these two we have discussed, right? And if we are talking about all subsets of R, all subsets of R means the real number. Okay, so now your hypothesis can be 1D, 2D, 5D, 7D, anything. Then its VC dimension is infinite. You cannot say that, because there will be something in the subset of R which can classify this data. This is the possibility. So if you are talking about the VC dimension is infinite, then it is not pack learnable, because you will not get a good probability of success. Okay, so this VC dimension concept is quite theoretical, so we have not including much details here. Okay, in fact in your videos also it is not included in very much detail. So now the concept of reinforcement learning. So till now we wanted to include some of the concepts which have theoretical which include theoretical concepts or theoretical approximations of machine learning algorithms, and these are specifically very much useful for those who generally work in theory, machine learning theory. Okay, so it's a specific branch which deals with only approximate solutions or approximate algorithms, especially for machine learning. So if you are interested in this field, you should learn these concepts. Okay, till now if you have any doubt, then please go ahead. Is my voice clear now? Okay, thank you. Maybe there are some disturbances from the device, so there are some magnetic resonance here. Okay, no problem. Now reinforcement learning. So reinforcement learning is a beautiful concept, because this reinforcement learning is actually, the learning comes from the human side, right? So reinforcement learning is a type of machine learning where an agent learns by interacting with its environment using trial and error and receiving feedback in the form of rewards and punishment. So till now in supervised or unsupervised type of learning, we don't have any trial and error method. We are optimizing using some method, right? And we have some of the idea that whether we have to match this with an output or we have to make some patterns. But here are some iterative procedures, and you cannot get the answer in just one throw, right? So for example, if I talk about you want to play chess, so chess is not like using just one moving some one of the candidate that thing in the chess, those what you say, those handles that you use in the chess. If you just play with one chance, it's winning or losing. No, it's not like that. It's an iterative, it's a sequential process. So generally reinforcement learning are useful for those areas where some sequence can be shown, right? For example, playing games, or for example some medical diagnosis, because medical diagnosis is not like if you have some symptoms, just you just stop there. No, it's an iterative procedure. You go to the doctor, you have some symptoms, doctor diagnose it, it gives you some medicine, then the effect of that medicine will help you to analyze your health, right? So the health monitoring or these things include reinforcement learning, not simple supervised and unsupervised approach. Okay, so as you can see from this diagram as well, so there is an agent. Generally we talk about agent. So this agent has some environment and it will take some action. So using that action, there will be some reward or punishment, right? So these rewards and punishment makes the agent intelligent. So how to do that? Let's see. So first of all, the basic comparison between these three. In supervised approach, you have labeled data with output and input. In unsupervised approach, there is no clear output. In reinforcement learning, you are not told the right answer. In supervised approach, you are told the right answer. For example, if I ask you one question, is it true or false? You will say, ma'am, it is true. Then I will tell you after that, no, you are wrong. You are the answer is not true. It is false, right? So I am here to supervise you. In unsupervised, you don't know anything. You make some patterns, and whether it will work or not, it will. Nobody has that clear output values. In reinforcement, you will tell me the answer, but I will not tell you the right answer. So if you will say, okay, for example, generally what we have in the vivas, right? So if I ask you some question, you tell me whether it is right or wrong, then I'll just give you the marks. You will get the marks only. You don't have the chance to mend your mistakes, right? You give me the answer, then I give you the marks. Next time you will say, okay, my marks are less. It means I have some mistakes. Where mistakes, you don't know. Okay. So in supervised approach, model learn to map input to output. Because if I am telling you it is true or false, or it is 1, it is 5, it is label flower, it is label machine, then you are able to grasp, right? You have to map your inputs with those outputs. In unsupervised approach, the goal is to find patterns, right? The clustering, the similarity, dissimilarity. In reinforcement learning, you interact with environment, try some actions, observe the outcomes, and then decide whether you want to repeat that action or not. So learning is driven by experience, not direct supervision. So let's say you wanted to learn a bicycle. When you try to learn the bicycle, no one has tell you this is the only correct way. They just show you one demonstration. You understand it or not, it's your choice. When you start riding the bicycle, then first time you will fall. You will get to know, okay, here I have to make this balance. I should not go in this direction. I should not grasp this handle in this way. I should use these tricks and tips for you only, right? So this is an experience, not a supervision. So here it is not supervised. No one gives you exact instruction, please move your foot 3 inch or till 2 degrees. No, it is not like that. It is neither unsupervised. You don't just watch the people ride and figure it out. No, you experience it. So it's reinforcement. You try, fall, learn not to fall. You get minimal feedback. Like if you fall, you will be having some pain. Then you will realize that, okay, I should not go in this way. Or maybe someone is there to clap for you. Okay, now it is good to go. So that motivation can help you build these experience, right? So this is how reinforcement is not like supervised and unsupervised. In reinforcement, trial and error is the key. So the agent tries different actions. So whenever you are trying different actions, you are exploring, okay, and it learns which action lead to better outcomes. So the actions which are leading to better outcomes, this is exploitation. You will repeat those actions again and again. So the delayed nature of rewards adds complexity, because sometimes rewards are not just after taking the actions. It will take some time. For example, you go to the doctor, you have some symptoms, they give you medicine. You don't have positive or negative reaction of the medicine in one day. You have to take it at least for 3-4 days after you get that reaction, right? If it is positive, then good. But if it is negative, then obviously maybe your health can deteriorate or something, right? So this adds the complexity. You might get feedback well after the action that caused it. Maybe you get the feedback right after that. Maybe that medicine is so much harsh that after taking one dose, you are not feeling well, right? So sometimes you get the feedback quickly. Sometimes it can be delayed for some time, okay? So this reinforcement learning origins comes from an experiment known as Pavlov's dog. So this RL is inspired by the behavioral psychology, like Pavlov's classical conditioning. So here what this experiment is, there is a dog and there is a food. So what the people has done, they keep this food in front of dog. So when the food is there, and the dog comes there, the dog's starting salivation. So this salivation means that dog want to eat the food. Okay, no problem. Now they change the food with a bell, because when the dog see the bell, it does not have any eating, this is not a thing to eat. That's why the dog was normal, no salivation was there. But if the food and bell are both there, so the dog starts salivation, because it gets an idea the food is there. So every time if you are giving this food and bell, each time you are giving these two things to this dog, it means dog has this sensitivity in the brain. Whenever there will be a bell, there will be food with for him, right? So that's how we train the animals, right? So whenever the bell will be ring, whether it is food or not, but the salivation will be there. So in this way we can say that the brain of a human, how it is working. So it is not approximately working to see the food or to sense the food, but it can work from the environment as well, right? So this is how this reinforcement learning comes from feedbacks and all. So it is not properly like if food will be present then only the dog can sense it. No, it is associating the food with the bell noise. So whenever the noise of the bell will be there, he will be there to get his food. Whether it is the food is there or not, it's then another thing. So modern field of was kickstarted by Sutton and Bartow. This Sutton and Bartow has a book of reinforcement learning named as reinforcement learning. This is the you can say a standard book if you want to read, whose 1983 work laid the foundation of today's algorithm and technique. So it's a big field. You can, if you are interested, you can start with this book as well. Now generally when this reinforcement learning,
Can we have the PDF copy of the book, ma'am?
yes, you can find it on internet. It's
Internet. Okay.
yes, if you will
Can you give the link for that any?
I can find that and give you the link, but this is the author name, Barton and Suto.
It's
Sutton
okay,
and
ma'am.
Barton. I can share in your drive as well. Okay. All right. So when this reinforcement learning started, it was started with the help of games, especially these indoor games, right? Because it these games has a lot of states. We can define some actions. We can define some agent, multiple agent, single agent. So this field is specifically started with this. If I say it's a Go player game, it's a Chinese chess game, which this field started to grow, and this is the major standard data set on which you can apply reinforcement approaches. Now this reinforcement learning is applied in every field, because as we live in the daily life, our work is not associated with a single stance of input. It has a series of input, right? So that's why it is now flourishing in multiple directions. So here games are the standard starting metaphor for reinforcement learning. So in chess, if you are told what move to play in a given situation, that's supervised learning. It means, let's say, in between of the chess, at this condition, what action you have to take is supervised approach. And if you just play without win or lose, or only get a reward at the end, that is called reinforcement learning, right? So you must figure out which moves lead to winning despite delayed rewards. So this is more like how human work. If when you start learning chess, okay, or any of the game you start learning, you will not win. You will try to observe, okay, I have taken this move, I should not do that. This lead to me to lose the game. So next time you become more and more intelligent. That's why we also say that practice makes a man perfect. So this practice lead to observe many of the situations or states after so much practice. And also, so this RL is also trained with many iterations, that in this situation this was the thing, in this situation I have lost, in this situation I have not lost. So at present, the internet, the online chess There was an chess player, I don't remember his name, who has beat that computer chess. Otherwise, it is so much advanced at this time right now that it's a important simulation tool that you can use to train yourself for this game, right? So here this reinforcement learning can be helpful. So here we can see that reinforcement learning involve an agent. It requires an agent learning through interaction with the environment. So in the chess there are multiple your moves, right? The handles you handle in those games. So for example, the environment can be helicopter, board, opponent. So it's more like that, right? So if the agent senses the state of the environment and takes action to influence it, so what the agent does, it takes what is in the environment and it takes some actions. Whenever it takes some action, some changes are applied, obviously. So key challenge is actions must consider long term benefits, not just immediate rewards. Supervised studies say that okay, at this position this should be done, but reinforcement learning say that I'm not talking about short term goals, I'm talking about the long term benefits, whether I will lead, whether these small steps lead me a winning state or not. It's more into this thing. So reward signal, the scalar feedback from the environment. It can be +1, it can be -100, it can be +100. It defines by the developer. Okay, so you can define 1 for winning and -100 for crashing. Just think about that. Okay, and biological analogy, you can say that this punishment and rewards are interpreted from sensory inputs. So for example, let's say if I talk about the robot, right? So robot, the task of the robot is to clean the surface, but whenever it will hit some any obstacle, some punishment will be there for the robot. Just think of a human in place of it. So if you want to train a human, when the kid start to walk, right, so it falls many times. So whenever he falls, some pain he feels in his body, that leads to a negative feedback. Then he start thinking, no, I don't have to do this, I have to make balance, then put my foot forward like this, then start in a small step, so then I can achieve the big time goal. Okay, so the key comparison on this basis is in supervised study we have input output, so we have target variables, so these are the same thing, right? But in reinforcement learning we don't have any target variables, we have some trial and error learning, so exploration is required. So for that there is a learning called temporal difference learning, because at each instance the states are changing of, whenever you take some action, states are changing, whenever you take some action, states are changing. So core idea is to predict the future rewards, updating the estimates based on the later prediction. So what we wanted to predict the later rewards, and we wanted to have an idea at this stage. For example, if I am playing a game chess and I have to think about, if I want to make this move, I have, let's say, 10 option of to make 10 moves, right? And I have to choose one. So what should be the optimal way that I choose so that it can lead me winning? As a human, I cannot go beyond 2-3 moves, because if you talk about some grand challengers or something, they have some idea because of their practice that if I choose to move this want to take this move, the opponent will take this move, then I will do this. Ultimately more than 10 moves cannot be put in your brain, but if you are talking about computer, then it has a lot more memory, so it can have some gradients store for that thing also. So that's why you can make your machine more intelligent than human. And this is only, I am giving you an example on the basis of games. Just think about if this thing can be applied in the field of medical. So if a patient is coming, the doctor can have an idea of, let's say, 10-15 patients in his mind, that this much this patient has these history, and if I give this medicine, how much the probability that the medicine will work, right? But if you have all this thing in this reinforcement learning, then maybe we can have some more better predictions. I'm not saying the doctor experiences will be going into vain. No, but it can help the doctor to take more better decisions, right? So the prediction at time t+1 is more accurate than time t. So for example, chess confidence in winning increases as the game progresses, but there is an update rule. Whenever you are talking about temporal sequences, there will be updation. So adjust earlier predictions using newer information. It reduces the winning probability from 0.6 to 0.55 if later evidence suggests lower odds. So it's more like that. It's a simple case of a day-to-day life where you think, okay, if I go in this way, I can reach the goal, or I will complete this task. But you don't know whether in between, in any of these moves, you get a backfire and you lose the game. It can happen also, right? You cannot predict all the things very correctly. So you just have to update the rules. Okay. So the biological basis here is similar to dopamine driven learning in brains. So for example, if I say for human perspective, if you go any unknown place, so you are quite I should say very attentive, and what is happening in your environment, you cannot sleep, right? But living in that place for some time, your brain start feeling safe. So it means that you understand your environment, you understand the things, and you go with a stable basis, right? So it's more like that. So an example is given here. For example, in the tic-tac-toe, let's say this is one state at this time. So you have three options, right? So now the opponent chance is to put a cross, and the cross can be put here, can be put here, or can be put here. So according to the three states, some rewards are there. So if you put here, you will get the reward 1. If you will put here, the reward will negative. If you put here, the reward will be 1, right? So in this way, we can choose which actions to be taken. It's more like that. And this is -1 because it will lead to some losing state, right? This state can or cannot be visualized with the help of training, right? So we cannot go beyond 10-20 states, but computer can do so. That's why this reinforcement learning is a good tool. Now next thing is exploration versus exploitation. So basically these two things are very important whenever we are going to choose for optimization. Why? Exploitation means choosing the actions with the highest known rewards. It means you have some knowledge, now you are choosing some state. It is called exploitation. Exploration means try suboptimal actions to discover better strategies. So whenever you are applying reinforcement learning, you don't take only single action. You take a set of actions, right? So you have in mind, let's say I have taken these actions. So if you are taking any suboptimal action, then it is called exploration. It means it may not lead to the best outcome at this stage, but maybe it can give you the better outcome. You don't know, right? So challenge is to balance this exploration and exploitation. So here there are the problems. If you want to learn in this field, there are some bandit problems. So bandit problems are more like that. A problem is there where the bandit had 2 hands, okay? Or we say that there are 8 bandits, each having 2 hands, and they have to for example, there are some situations given to them that if they pick up one refrigerator, then they cannot pick another object, and they have to pick in such a optimal way that they can have the you can say that most costlier items, right? So this is called bandit problems. So there are, in another way you can have an idea, there are multiple machines, ATM machines, and some line is there. So how you will manage that line? It's more like in this form you can say. So the bandits can be your ATM machines, and the data is coming in the line like people. So in example, in tic-tac-toe, occasionally pick random moves to avoid repeating the suboptimal paths. So if you don't know anything where it is leading or not leading, then you choose some random paths which is called exploration of any algorithm. Okay, so this is all about reinforcement learning. Basically, we have not include much of the details here. We have just include that this is to be learned. So it's a big, it's a more like small concept here. But I want to show you one question which is related to reinforcement learning, and it's more like this one. So here for this question they say that we will follow a simplistic game and see how reinforcement learning agent can learn to behave optimally. Okay, so this is their game. The rules are defined. Rules is at the start of each game the agent is on the start state and can choose to move left or right at each turn. Okay, so every time agent is on the start state, it has to be chosen whether it will go left or it will go right. Okay, if it reach here RE it will win. If it reach LE it will lose yani -1, RE yani ki +1. Because we love math so much, instead of saying that agent wins or lose, we will say that agent gets a reward of +1 at RE and reward of -1 at LE. So they have defined these rewards +1 and -1. Then the objective of the agent is to simply maximize the reward it obtained. So we have to just choose a strategy which can maximize this reward. Okay, so now the question is, for each state we define a variable which will store its value. So basically we have to store the rewards, so we will define a variable for that. So what is the variable name? The variable is value. So the value of the state will help the agent to determine how to behave later. It means each state will have a value variable, if and for that value of the state will help you to move either in left or right. So first we will learn how to define this value variable. So let's V is the mapping from state to its value. So what is the value? The value of LE is -1, value of RE is +1, this one, and another state's value is 0. And how you will move? The moving strategy is giving as, for each state there are these states x1 to x4 and start, with SL being the state to its immediate left and SR being the state to immediate right. It means for start this is your SL and this is your SR. SR means state right, SL means state left. So we define the value of each state. When you update the value, it's 0.9 multiplied by the maximum of the value of left and right. It means whenever, if you are at a state, let's say you are at a state here, so you will take the maximum of x3 or RE multiply by 0.9 and give that value to this state. It's more like that. Okay, so we will update the states till the V is converged, or we cannot change any of the states. It's more like that. So question is, what is the value of x4 after one application of given formula? Okay, so we have to define the value of 4, this 4, and it is in the initial of formula. So let's say our agent is at x4. What is the value of 4? The maximum of the value of this or this multiplied by 0.9. So this has the value 1, this has value 0. So the maximum of this value will be 1 and you multiply it by 0.9. So this will be the value of x4. So we will say this, the value of x4 is 0.9 into maximum of x3 or RE. So the x3 is 0, RE is +1, the maximum is +1. So +1 into 0.9 is equal to 0.9. So answer is 0.9. Is this correct? Is this clear to you? Is this question clear? Okay. So can you tell me the answer for, what is the answer for x1? What will be the value of x1?
It should be 0, right, ma'am?
Correct. Okay, so this is the same question. What is the value of x1 after 1? It will be 0. Okay, you got that. Now the question is, what is the value of x1 after v converges? V converges means you have reached here. Okay, v converges means you have reached here, you win the thing. So it means that, just think about this, if you had win this state, you have reached this state, then obviously you have reached from here. Okay, from x4, x4 पे कहाँ से आए होगे? x3 से, x3 से कहाँ से आओगे? स्टार्ट से कहाँ से आए होगे आप? x2 से, x2 से आए होगे आप x1 से. ठीक है, so it means that you have to evaluate all these three in the backward position because it is converged, right? So after convergence, just think about this, the we take it from the left right hand side. So what is the value of x4? You have already calculated 0.9 because it is 0, it is 1, this is 0.9. Okay, if we calculate the value of x3 now, its value is 0.9 at this time. What will be the value of x3?
Point 81.
Yes, it means multiply by 0.9. Okay, because this is the highest value. Now to calculate the value at start, you here it is 0.9 into 0.9, so again 0.9 to the power 3, right? Its value will be 0.9 to the power 4 and its value will be 0.9 to the power 5. So that's how you can have the value of x1. It will come as 0.59. You can check it out. Okay, it's 4, it's 3, start, 2 and last one. So these are the questions that was there. So this was the last slide and I will include some more questions if I get, but this is now what I am having. It's a request that please fill this feedback form if you have any questions other than the given topics that I have discussed in the last lecture. It means you have put the feedback for variable elimination and that Bayesian trees. So apart from that, if you need any practice or something, then please fill the feedback by tomorrow so that I can prepare for the next Sunday. So next Sunday, this Wednesday, not Sunday, Sunday will be the last class which we will be having the extra section. Now if you have any doubt, then please go ahead.
Madam, when will be the next class, ma'am?
Next Sunday.
Okay, okay, madam. Right.
Next Sunday, same time, same day, we will have our last class. And if you have any doubt, then please go ahead. Otherwise, thank you so much for patiently hearing these lectures. I know there are some audio.
Thank you so much, ma'am.
Thank you very much for.
Sure. Thank you so much.
Thank you.
Okay, thank you.